In question 13, a sound waves were reduced in its intensity. So if we reduce the intensity, what will happen to the wave amplitude? The amplitude will also decrease. And it has a constant frequency. It has a constant frequency means like the vibration number of waves per second has not changed as it travel through the air. So which statement is correct? The maximum displacement of the particle changes between one particle to the next particle. Because when we change the amplitude, what is the meaning of the term amplitude of the sound wave? The amplitude of the sound wave is refers to the distance between two particles. Like, and the maximum displacement is called, the maximum displacement is amplitude. So this is the maximum displacement we call amplitude. So if I reduce the intensity, what will happen to amplitude? The amplitude will also decrease. So means the space between the two particles, if the amplitude is decreasing, the space between the two particles will also decrease. That's why when we select the option here, that in question 13, the maximum displacement between the particles changes from one particle to the next particle, that is the right answer. But what about option B? The phase difference between the adjacent particle is zero. The phase difference between the adjacent particles when you are comparing the motion of the particle, as you can see, observe if one particle is moving towards right, the other particle is moving towards left, the motion. While observing this particle, like this particle move right, then this particle move left. So when we compare these adjacent particles, they're not, if their phase difference was zero, it means all together will move at the same time. But they're not all together moving. Like what happened? First, this particle pushes the other particle, then it pushes another particle and transferring the energy. So the phase difference or the angle difference between the two particles is not zero. Is it clear? The second point. The wavelength is the distance between the two particles that have a phase difference of 180. When we compare the group of the particle, as you can see, the two particles, when they are one wavelength apart, what is the phase difference between them? If you see, just focus on any one of the particle. Let's say we focus on this particle. An identical particle, this looks another identical particle. Let's focus how they're moving. So when you compare the motion, the phase difference between them, if one particle is moving left, the other is moving right. Or so the two particles are actually what they're moving. They're not moving 180 out of phase. They're moving in the same way. The wavelength is the distance between the two particles. Have the phase difference of 180? No, it's like one wavelength apart. The particles are moving in the same manner. And the next one, the two particles have a phase difference of 360, have the same maximum displacement. Means if two particles are moving in the same way or vibrating in the same way, they have the maximum displacement. It's not the case. As you can see, in a sound wave, when the phase means like a mode of a vibration. When these two particles are moving towards left or a right, like as this group of a particle, these group of a particle are moving towards right, so they don't have the same distance. Like here distance is different, here distance is different. So for a sound waves, actually what happened when a vibration produced, the spacing between the particle changes. Maximum spacing is known as amplitude, but its amplitude vary. Like its displacement, I mean vary, not the amplitude. Amplitude is a maximum displacement. But you can see these group of particles are moving towards right. but they don't have the same distance. Here, the particle have different maximum displacement, this different maximum displacement. Here, the particle have the highest maximum displacement, what we call amplitude. So when the particles are in phase means they're moving in the same manner, all are moving in the same manner, but the maximum displacement is not same. Here, the maximum displacement, let's say 2 centimeter, here it will be 3 centimeter, here it will be 4 centimeter. And this maximum displacement is known as amplitude. So the option D, which state that the two particles have a phase difference of 360, have the same maximum displacement, that is not correct. The two particles may be moving in the same manner, but they don't have the same maximum displacement. How are the particle moving in the same direction? I thought you said that. No, the particle, the group of the particle, when you observe in a sound wave, focus on the group of particle. One group of particle is moving towards right, another group of particle is moving towards left. So for that group of the particle, if we focus on one, like we are focusing on this one, this area. When you focus on this group of particle, first they move left, then they move right. Then they move left, then they move right. So when they're moving left or right, you can clearly see the spacing between this group of particle is not same. They all are moving in the same direction, but they don't have the same displacement. And this group of a particle is moving, when you focus on other group of particle, they are moving on the opposite, in the opposite direction. So one group is moving left, one group is moving right. If one group will move right, the other group will move left. But the spacing between those particles which are moving in the same direction, that is not same. The term 360 means that they move in the same direction. They have the same way they are vibrating. That is the meaning of a 360. And what is the meaning of a term 180? A phase difference of a 180 or anti-phase means they're moving in opposite. Like if one particle move towards right, one particle move towards left, I'll say that they have a phase difference of 180. But if two particles are moving in the same direction, same manner, so I'll say that they have a phase difference of 0 or 360. So they're saying that the two particles which are having a same phase difference have the same maximum displacement. That's not the case. The group of the particle which are moving, one particle move maybe 2 centimeter, another 3 centimeter, another 4 centimeter. So even the group of the particles, 360 is not out of phase, 360 is called in phase. 0 and 360, 0 degrees or 360 is called in phase. 180 is called anti-phase or out of phase. So in a sound wave, when the particles are moving, one group of a particle is moving towards right, another group of particle is moving towards left. And if they are moving in, the group of particles are 180 out of phase, but this region of a particle, adjacent particles are in phase. And this also in phase. But compared to these two groups, they are anti-phase. So the term phase refers to a mode of a vibration, like how the particles are moving. Question 14, any doubt? Question 14, what is the amplitude? Amplitude is the height. So what is the height of this wave? It is 3. So we write 3. How to get the wavelength? They mention it's an electromagnetic wave. So what is the speed of electromagnetic wave in a vacuum? They all have the same speed, 3 into 10 to the power 8 meter per second. We need the wavelength. So speed is frequency times the wavelength. Or frequency is the reciprocal of the time period. So I can say speed is 1 over time into wavelength. Time period is divided, other side multiplied. So speed multiplied by time is equals to wavelength, time period. Speed of the wave is 3 exponent 8. What about the time period? The time period is a time to complete one oscillation, you can start from here, from one trough to another trough. Like if you start from here, this is one complete oscillation. Or you can also start with one complete wave, one complete crest, and one complete trough. So it start from 5 and ending at 25. So the duration is 20 microsecond because it's a unit is micro. So it's 20 microseconds. So 20 into 10 power minus 6. So we just have to multiply 3 exponent 8 multiplied by 20 micro 10 to the power minus 6. That will give us a wavelength. 3, which is equivalent to 6,000. So it matches with option A. Next, we have question 15. Any doubt? A question 15 is actually, it's the same question as we did the first one. Like, I mean the third one. It's the same. How to do this? Whenever you need the frequency of the or the wavelength of the original wave, you have to subtract the two patterns. In the question, a long glass tube is almost completely immersed in a large tank of water. A tuning fork is stuck. So tuning fork is actually a source for us. And it is held just above the open end of a tube and it is slowly raised. A loud sound is heard when the height, first what it will be? It will be a closed pipe. Why it is a closed pipe? Because one end is a reflecting. Like a tuning fork produces a sound wave. This sound wave will travel, strike the water surface and bounce back. When two waves which are traveling in opposite direction, it gives rise to a standing wave. So the first pattern of a standing wave is observed. So in the question, we observe the first pattern of a standing wave when this height was 18 centimeter. So when we'll observe the first pattern of a standing wave, here we'll have antinode and we'll have a node and this will be the pattern. So this distance is how much? This is in terms of the wavelength, it is a quarter of the wavelength. Okay. Which is equals to 18.8 centimeter. Then the second pattern is heard. We have the same tube, which is raised slightly out from the water. And the second pattern is observed. So when we observe the second pattern, what is this? This is, and there will be antinode here, node here, antinode here, and node. So this will be the second pattern. And how much is this in terms of the wavelength? It is 3 by 4 wavelengths. Why 3 by 4? Because distance between the node and antinode is a quarter, and between the two successive nodes is half. So quarter plus half, it will be 3 by 4. So the 3 by 4 wavelengths, in terms of the wavelength, 3 by 4 wavelength is equivalent to what? This was equivalent to 56.4 centimeter. When we take the difference of the, like, look, this is a wavelength of the first wave, this is a wavelength of a second wave. The wavelength of a pattern is different, but we need the wavelength of the source. So whenever we need the wavelength of the source or the frequency of the source, what we simply do, we subtract the two patterns to know the actual wavelength. Because the difference of the two patterns will give us the wavelength of the source. So if I subtract them, like I have 3 lambda by 4 minus lambda by 4, and in terms of the distance, it was 56.4 centimeter minus 18.8. So when I solve this, this will be equals to 2 lambda by 4 or lambda by 2. So this is lambda by 2. And when we simplify this, 56.4 minus 18.8, what's the answer? 56.4 minus 18.8. So that is equals to 37.6. 37.6 is there. Now 37.6 multiply by 2. But this is in centimeter. We have to divide by 100 to convert into meters. 0.376 multiply by 2. So the wavelength, because this is lambda by 2, so this will be multiplied. So 0.376 times 2, that will be 0.752. Okay. So 0.752 meters. Now we know the original wavelength of a wave, because this was a wavelength of the first pattern. This is the wavelength of the second pattern. When we always subtract the two consecutive patterns, we got the wavelength of the original source, because wavelength of the original source is not changing. Only the standing wave changes according to the distance. So this is the original wavelength of a wave. Now, we need the frequency, because the original question is about the frequency. So you have the formula V is equals to F lambda. The speed of the wave is 330. The frequency we don't know. And what about the wavelength? It is 0.75. So 0.75, 0.752, it is multiplied. Other side will be divided. So 330 divided by 0.752. We got the frequency, and that is 438 hertz. So it matches with option B, which is 440 hertz. So again, if you see, it's a repeated question, a same pattern. Whenever you need the frequency or the wavelength of a source, you will work out the wavelength of the first pattern. You work out the wavelength of a second pattern. You subtract the two wavelengths to know the original wavelength. And original wavelength and the speed is there, so you can work out the frequency. Is it clear? Question 16, any doubt? It's related to a Doppler effect, the relative change in the frequency. Question 17, any doubt? Question 16. Yes, sure, I will explain question 16. Question 16 is related to a Doppler effect. What is a Doppler effect? A Doppler effect is actually a relative change in the frequency when the source or the observers are moving. If they are moving towards each other, the frequency heard will be higher. If they are moving away from each other, the frequency heard, like the number of waves received, will be less, and the wavelength will be longer. So, and if you want to work out the frequency observed, that is the frequency of a source, the speed of a wave divided by speed of a wave minus speed of the source. If it is moving away, this will be the case. But if it is moving towards, the denominator will get larger if the source is moving. So this is when it is moving away, and this is when it is moving towards. So usually when it is moving away, the frequency which we receive will be higher, and it is moving towards, the frequency which we receive will be shorter, like smaller frequency. Now, the source is emitting a sound with a frequency of Fs, and it is moving at a constant speed. Yeah, if it is moving towards, I mean the same thing. If it is moving towards, it is higher, and it is moving away, because when it is moving away, the frequency will be shorter, like lower frequency. So in the question, it is directly moving towards the observer. So let's say this is the observer, O is there, and here is a source. The source is moving towards the observer. The frequency which the observer will hear, that depends on the source frequency. That depends on the speed of the wave which is produced, like it's a light wave or a sound wave, that's a speed, divided by speed of a wave minus speed of the source. So in the question, they mentioned that it is moving at a constant speed. So if it is moving at a constant speed, this will not change. The speed of a wave is a constant, that is not changing, and the speed of the source is also not changing. But the only difference what will happen, the observed frequency will be higher. So the observed frequency will be higher, but the observed frequency will not change. Why? Like, I mean to say observed frequency will not change. What does it mean? Let's say the frequency of the source was 100 hertz, but frequency received by the observer will be higher. He will receive more than 100 hertz, but like let's say 120 hertz, but he will receive 120 hertz throughout. It won't change. Why it won't change? Because the speed at which the source is moving, that is not changing. The speed of the wave is constant and the source frequency is also constant. So in the first part, the frequency will be higher, the observed frequency will be higher, and it won't change. The second part, when the source is moving away, so if the source is moving away, the formula is the observed frequency is the source frequency divided by V plus Vs. So again, the speed is not changing, like the frequency which is heard, that frequency will be shorter. So if the source is, let's say, emitting out the same 100 hertz, but what is received by the observer will receive a smaller, less frequency, let's say 80 hertz, but it will be remain 80 hertz. It will not change. Why it will not change? Because the speed of the wave is not changing. The speed of the source is also not changing. So the change will be there, but it will be a constant value. So which one it matches with? It matches with option B. Then the frequency heard will be higher than the observed, then the frequency observed will be lower than the observed, and when it just crosses the source, or when it is just next to the source, and that like the source is next to the observer, it will be the same as the frequency of the source. Is it clear? What about this scenario? This will be the scenario F naught is equals to Fs, velocity of the speed of the wave, minus Vs. But what will happen if the object were accelerating? Like if the speed of the source was increasing, if the difference here will get smaller. So I mean this, if an object is decelerating, because this is the observed frequency. So the observed frequency is equals to V divided by V minus Vs into Fs. Fs is a constant thing. These are constant. The only difference which make is the speed of the wave. If the speed of speed of the source. If the speed of the source increases, here the difference will get smaller. If a difference is get smaller, the frequency observed will get much higher. And the same thing, if V minus Vs, if the source is decelerating or the speed of a source is decreasing, what will happen? This difference will get larger. If this difference will get larger, the frequency observed will be smaller than what is actually emitted out. So you just remember the source formula, not the observed formula. Like not for observer motion. It's always the source will move. Yeah, No, I'm giving the same idea. If the source, let's say there is a source which is moving towards the observer and the speed of the source is increasing or decreasing. So if a source is moving toward in a Doppler effect, because in a Doppler effect we have the concept is one is it's moving towards or away, another one is it's moving towards but with a different speed. Like here is an observer, here we have a source, this is also a source. This source is moving away, this source is moving towards. For source 1 and for source 2, the formula for observable, like the person observing this, so the frequency, observed frequency is the speed of a wave minus the speed of the source in the denominator multiplied by fs. But for the second one, the formula is it's a addition into source. That is when it is going away. This is when it is moving towards, the two cases. But what I was giving an example, let's say it was moving towards, but different, with it approaching with a different speed. Like in this question, they mentioned it's moving at a constant speed. But what if it was approaching, but with a different speed, like its speed is getting higher? So if it was approaching with a higher speed, accelerating, so what will happen to this denominator? The denominator will get smaller. So the frequency observed will get higher. Means what we will get? It's more. So the graph will be like this. The observed frequency will get higher when it is moving towards. The frequency is higher, but as it is accelerating, the observed frequency will get higher. And if it is approaching and the object was slowing down or decelerating, if the speed was decreasing, so this will get higher, like it is approaching, but with decelerating, slower speed. So if it is getting slower speed, so the frequency observed will get smaller. So when it is accelerating and approach, like moving towards and accelerating, this will be the graph. When it is moving towards and decelerating, then this will be the graph for the observed frequency. And let's say this is a source frequency. Is it clear, this idea? So in question 17, any doubt? Question 17 is related to the names of, you have to learn the order, like as I mentioned, the wavelength order to answer this. Question 18, any doubt? Question 18, a standing wave is shown. 18 and 19. The diagram shows a string stretched between the fixed point of x and y, and a stationary wave is produced. If a stationary wave is produced, this is a node, antinode, node, antinode, node, antinode, node, antinode, and node. How the particles are moving between the two adjacent nodes, they are moving in the same way, but the particle opposite to the nodes, they're like moving in opposite direction. That is a motion in a standing wave. So we have to identify which statement is correctly explaining this standing wave. A solid curve, the solid curve shows the string positions and the string is continuously vibrating. The dash curve shows the other position of a maximum displacement. The straight central dash line shows the mean position. The point S on a string is directly above point P, and the point T is on a string is directly below point Q. Which statement is correct? A short time later, R on the string will be displaced. R is at the node. The particle at the node in a standing wave. Will they move? No. The particles which are at the node, they will not change their positions. So any particle here, let's say A, B, C, D, these all particles will remain at their place. They won't change their position. So I mean this statement is not correct. The point S and T are moving in opposite direction. So point S and T, are the particles moving in opposite direction? Or the string is moving in opposite direction? Yes, they are moving in opposite direction. That's why B is the right answer. What about C? The distance between P and Q is one wavelength. The P and Q is actually like, if you compare, this is an anti, when you compare the position, this is like antinode and this is also antinode, the horizontal distance. So the distance between the two successive nodes or two successive antinodes for a standing wave is not equals to one wavelength. It is equals to half of the wavelength. 2 points on the string, they are equal distance from point R vibrating in phase. So 2 points which are equal distance. Like example, if one point is say 1 meter up, 1 centimeter above, another one is 1 meter below, 1 centimeter below. Are they moving in the same direction? No, they are not moving in the same direction. They are moving in opposite direction. So the particles on the opposite end of the nodes or opposite end of the end, their nodes are moving in 180 out of phase. So if this particle R is there, so group of particles are going down, so this group of particle will go up. Or if this group of particle is going down, this group of particle will go up. That's why D is also incorrect. So B is the right answer for this. Question 19, any doubt? Which statement must be true for a diffraction occur when a wave passes through a gap? If you want to observe a diffraction, what is the condition for a diffraction? Diffraction happen or occur for waves which are moving. Moving wave, like wave must go from one place to another. If a wave is traveling from one place to another, then it can only diffract. The wave is able to travel through vacuum. Diffraction can happen in the sound wave. Wave cannot travel through vacuum. So this is not a must true statement. Like it should be true for all cases. So the progressive wave means the wave which travel from one place to another can diffract. So that is always there. Like it should always be there that there must be a moving wave that it passes through the gap and it can spread out. So progressive wave can undergo diffraction. It's always the case. A wave has a large amplitude, even it has a large or a small amplitude, but that is not the case. It can diffract even a small amplitude depending on the gap size. The wave has a longer wavelength. Shorter wavelength can also diffract because diffraction not only depends on the wavelength, it also depends on the gap size. So diffraction progressive waves must pass through a gap to diffract. Question 20, any doubt? Twenty 21. Question 20. Whenever it's a double slit experiment, what is our formula in a double slit experiment? Lambda is equals to AX over D. What is A? A is the spacing between the two slits. What is X? X is a distance between the two successive fringes, two successive maximas or minimas. That is X. And what is D? D is a space between the slit and the screen. And what is a lambda? Lambda is a wavelength. So lambda is AX over D. So where A is a spacing in the question, spacing is 0.2 millimeter apart. So 0.2 into 10 to the power minus 3 because it's a millimeter. So 0.2 into 10 to the power negative 3. X is a spacing between the fringes. Observe 5.4 meter. Sorry, this is X because I read the interference pattern observed on the screen, that is 5.4 meter. This is 5.4 meter. So X is 12 millimeters. So this will be 12 into 10 to the power negative 3 and divided by 5.4. You'll get the wavelength of the wave. What's the answer here? You just have to, whenever a double slit experiment is there, we use this. When grating element is there, we use d sine theta is equals to n lambda. Which one it match with? So it matches with option A. 4, yeah, it's 4.4. It is 4.4 into 10 to the power minus 7. When I convert, like I move point one, two places, so this will become 440 into 10 to the power minus 9. Minus 9 is nano. Like when I convert, so it is 440 nanometer. 4.4 exponent minus 7. When nano, on your calculator, there's a button E and G. When you press that E and G, it will give you answer in a multiple of 3, like power 3, power 6, power 9, power 12, power 15, and so on. Question 12, a diffraction grating in a screen is used to determine a single wavelength of a light from a source. What is the essential feature of this experiment? What is the essential feature of a diffraction grating? The curved screen must be used. No, that's not the case. We use a linear or a plane screen. The diffraction angle must be measured for at least 2 interference maxima. Like example, we have a first maxima, then second maxima, third maxima. It's not like must. If the diffraction angle theta must be measured for at least 2 interference maxima. Like when we are measuring a theta, we should measure for maximum, like at least minimum 2 times. No, that's not the case. The light wave incident on a grating element must be coherent. You cannot observe the interference pattern of a grating element if the light wave is not coherent. Coherent means they should have a constant phase relation. Like if one is crest, other is trough, but it remain like that. So then the waves will diffract and you can all observe the interference pattern. So essential feature to observe the interference pattern, the light which are incident on the grating element must be coherent. You cannot observe a constant pattern of these fringes if the wave is not coherent. The third order intensity maxima must be produced. No, that's not the, it can be fourth order intensity maxima can be produced for 5 order. It totally depends on the D and the wavelength which we are using. But what is the essential feature? That the light which we are using, which incident on the grating element, it must be coherent. If it is not coherent, we cannot observe the interference pattern.